Hello everyone, this video is a coursework submission for my DSA module. I'm going to talk about the stable matching algorithm, which is also known as the algorithm of happiness, because it literally tells you who's the best person you could possibly marry. I hope you enjoy this video and find it somewhat helpful. So in this video, I'll first explain what is the stable matching algorithm, and then I'll walk through an example solved by this algorithm. After that, I'll adduce some real-life applications and many more problems this algorithm can apply to, and we'll end up with a brief discussion of its computational complexity. To start with, what is stable matching algorithm? In 1960s, David Gale and Gale-Shapley proved the solvability of stable marriage problem. That is, for an equal number of men and women, it is always possible to pair up every man and woman and make sure all marriages are stable. They presented an algorithm to do so, and this algorithm is named after them. You may wonder what is meant by stable. Well, a stable matching is where there doesn't exist any alternative pairing, say A and B, where both A and B prefer each other to their current partners. If so, there's a danger of them, both abandon their current partners and run away together, leaving behind some ugly and heartbroken scene. So, a stable matching is where there's no unstable matching at all and everyone's satisfied with his or her current marriage. Okay, so how does this algorithm work? Before pairing up, everyone, both men and women, need to come up with a preference list of the opposite sex. This list must be a strict list which includes all of the opposite sex and ranking them with no ties. Everyone is supposed to be honest and stick to the preference list with respect to proposal and acceptance. After preparations on the first day, say in the morning, each man proposes to his top choice on his preference list. In the afternoon, some women may be in the happy situation where she received one or multiple proposals. She'll have to reject all but her top suitor, to whom she says maybe. The rest of the unlucky women remain unengaged. To note here, by replying maybe, the woman is provisionally engaged with this suitor, and so he cannot propose to other women, obviously. However, women can dump him if at a later stage a more favored guy shows up and proposes to her. That's why a woman says maybe instead of confirmative yes. This may sound awful for men, as he seemed to have wasted his time and got dumped in the end, but we'll discuss the fairness later. The algorithm is actually to men's advantage, giving men the best match possible. Okay. So on the second day, third day, and every day after until everyone got engaged, the algorithm runs iterations. Every morning, each man who got rejected the previous day needs to pull himself together and propose to his top remaining choice, regardless whether the woman is engaged or not. Each afternoon, woman rejects all but her updated top suitor. Repeating the iteration day after day until every man got engaged, the algorithm then terminates. So now I'm going to show you an example of this algorithm. Suppose we're now pairing up 4 men with 4 women in a stable fashion. Here we got Zach, Jan, Will, and Victor. For girls, we have Amy, Betty, Carol, and Daisy. Each of them has armed with a preference list of the opposite sex. Left table are males' lists and right table are females'. 1, 2, 3, 4 are the order of their preferences. I put their initials instead of their names just for simplicity. Let's take Zach for instance. This table shows he prefers Amy to Daisy to Carol to Betty. So let's get started. On the first day, each guy proposes to their favorite lady. Lucky Amy received 2 proposals from Zach and Jan. Betty got it from Will, and Carol got it from Victor. Amy prefers Zach to Jan, so she replies maybe to Zach and rejected Jan. Well, Betty and Carol says maybe to Will and Victor, respectively. At the end of the first day, each man except Jan got provisionally engaged. The second day, Jan proposes to his next top choice, which is Betty. Unfortunately, Betty favors her current partner than Jan, so Jan got rejected again. On the third day, Jan hasn't gave up, he goes to Carol's. It turns out Carol prefers him to Victor, and so she dumped Victor. On the fourth day, Victor proposed to Amy, but got rejected, as Amy still prefers Zach. On the fifth day, Victor proposes to Betty. In consequence, Will got rejected and begs the market. On the sixth day, Will proposes to Daisy. Daisy was devastating. After 6 long days, she finally got a suitor. She accepts his proposal and 2 of them becomes engaged. So now 4 guys are all got engaged with a woman. No one is left alone. Zach with Amy, Young with Carol, Will with Daisy, Victor with Betty. The algorithm terminates here, on day 6, or after 6 iterations if you will. Happily ever after. Okay, now I'm going to talk about what kind of problems stable matching algorithm can apply to. First of all, the stable marriage problem, of course, as shown in the example. We got everyone a stable marriage. As I mentioned before, it also guarantees every man has got his best possible stable match. Why? Because men are the ones who proposed, who made the move. They always propose to the top of their remaining list. If he didn't manage to engage with someone he prefers, it means he got rejected by her already. That match wouldn't have been stable after all. So in the end, men always got the best possible valid partner. But this is not the case for women when there exists more than one possible stable matchings. That's right, the stable matchings are stable but not always unique. And in these cases, men got their best and women got the worst. Apart from marriages, this algorithm can apply to a group of problems as long as it involves 2 sets of elements of the same number and try to map all their elements in a 1-to-1 correspondence. And make sure they're stable, of course. The most famous real-life application is assigning graduating medical students to their first hospital based on a preference list of hospitals among students and vice versa. A significant number of countries are using this algorithm for it. Also, similar schemes like assignments of secondary school students to universities and primary school students to secondary school in Norway and Singapore respectively. And examples like dating websites, applications to internships, and many more. So finally, I'll briefly talk about the computational complexity of this algorithm. The stable matching algorithm terminates after at most n² proposals, giving n men and n women. An easy but not so proofy explanation is that for n men and n women, there are at most n² possible matching schemes, because this algorithm guarantees everyone got a match. So imagine the worst case. A man got rejected every time until the last one. He proposed n times in total. Worst case worse, every man went through the same thing. That n men all proposes n times to get engaged. That is n² proposals in total. Therefore, we can say the algorithm is upper bounded by an n² behavior. So, that's pretty much it. I hope you have got a rough idea of the stable matching algorithm. I really appreciate you stay to the very last minute of this video. Thank you for watching.